Hello everyone, I'm Castro. Today I'm here to present you our work on displacement-based multi-modal formulation of Koiter's method applied to cylindrical shells. I had the pleasure to carry on this work with my colleague Elko Jansen. Koiter proposed a method that can be used to calculate a reduced order model for the displacement with respect to the load in cases where we have a nonlinear dependency, as in this example. Koiter's nonlinear asymptotic expansion starts with defining a linear or nonlinear pre-buckling state and then adding to this pre-buckling state contributions from the linear buckling modes and second order modes. These factors psi can also be calculated as a function of the load level and also using the contribution of A and B factors that we'll discuss later. The procedure basically consists on defining the load level in which you want to evaluate your displacement field. Then you calculate the psi factors that depend on lambda. And finally, you can obtain a reduced order model U in terms of lambda and the psi calculated. Now let's look into more detail on how can we calculate the first and second order modes and also the A and B factors. In the case of a multimodal analysis using only two modes, we will have two linear buckling modes. Then we'll have three second order modes. We'll have, in the more general case, 8 A factors or A coefficients, and also in the more general case, we'll have 16 B coefficients. In this example with only two modes, given a load lambda, when we calculate psi1 and psi2, these are the equations that we obtain. So we have two equations for two unknowns, which are psi1 and psi2. This can be solved non-linearly. With now psi1 and psi2 calculated, we can build our reduced order model for the displacement field U. And given that we know the pre-buckling state, which was calculated with a linear or nonlinear static analysis, we are now ready to calculate our displacement vector at the desired load level lambda. To calculate our A and B factors, we use the equations shown on this slide. The derivation of these equations is discussed in more details in the manuscript. What I want to emphasize more in this presentation is the presence of these higher order derivatives of the total potential energy functional. Here I want to discuss a bit more the formulation and especially the notation that we decided to use in the displacement-based formulation. We obtain the higher order tensors with the Fréchet's derivatives. Given in the simplest case of a uniaxial stress and uniaxial strain, and then we can obtain the total potential energy functional, assuming that there will be only contribution from the strain energy. This would be the equation that we have. So basically integrating the multiplication of the strain and stress over the volume. When we calculate the first variation, that could be, for example, with the purpose of obtaining the stationary point of this energy functional, we would result, usually we use just the variation of phi, and Fréchet proposed that we can calculate a variation of phi multiplying the variation of the independent variables. In this case, they are the displacement field variables. And then we can represent that also as a variation of our energy functional. Here I'm already assuming that the stress can be expressed in terms of the strain, multiplying the constitutive relations. And then we can also represent the first derivative of this strain functional with this prime. And note that we moved from a scalar quantity to now a multiplication of a vector and another vector. Going further with the second variation, which is used, for example, in the case of the neutral equilibrium criterion to calculate linear buckling, we would also be able to represent it as a second order tensor multiplying two vectors from left and right. So up to the second order, it is possible to represent this multiplication using the transpose symbol quite simply. We'll see on how this becomes more complicated for higher order derivatives. So now extending the second variation for the strain and stresses, we would have the following equation where this term would represent the nonlinear constitutive stiffness matrix. It would result in the nonlinear constitutive stiffness matrix, and this term would result in the geometric stiffness matrix of the system. This can also be represented now using Frechet's derivatives, as I'm highlighting here now. So note that I have here one vector multiplying another vector in a way that this would create a second order tensor, and also here we have a second order tensor multiplying scalar. Now if you want to calculate higher order derivatives other than second order, you will see that the notation using transpose and not transpose becomes very limited. And therefore, I propose in the previous paper to use these sub-indices A and B to represent the order in which we are multiplying the higher order functionals by the respective vectors. So here, if I have a second order functional, I can multiply it by vector A, B in this order, for example. And this could be extended to third order quite easily. So the third variation of this strain energy functional would result in this expression. So using this sub-index notation, we just add the indices accordingly to the order in which we apply the variation, and then this term would become a sum of this term, and this term would become a sum of this term and this term. We notice that for all the strain relations that we have been using, that the third variation of the strain or the stress would always result in a zero. So applying the fourth variation to find the fourth order tensor that is involved in Koiter's asymptotic expansion, and the methodology to calculate the B factors would then result in this equation, already considering that the third variation of a single element would always result in zero. We have here the outer multiplication of second order tensors resulting in fourth order tensors, represented in a way that keeps the order in which we applied the differentiation. So if I want to multiply this, the result of this outer product with respective vectors, I can just use the vectors in the same order in which the indices are kept here. This will be exemplified later in a code. This slide compares our formulation already for the case of the cylindrical shell being investigated in the manuscript with the implemented code. You can see how the code keeps a very close relationship with the formulation. In this example, I'm multiplying this stress second order tensor twice, first by UB and later by UA, and it was easy to find the right order of the multiplication because we kept the indices notation here while applying the higher order differentiations. You can also see that for other parts of the code later, comparing the paper with the dataset that we provided. So about the dataset, it was made available already on Zenodo. You can find the link using the references that we provided when we cited the dataset in the manuscript, and I welcome you to explore this code and possibly even to contact us if you want to collaborate doing research in this direction. So thank you for your attention. I hope you also enjoyed the manuscript and also enjoyed the conference, and I hope to talk to you soon. Goodbye for now.